In this lesson, we're going to look at atomic structure, which means how the atom is put together and what it's made out of. Now, some of this is just a review from last section. We know that the atom is composed of protons, neutrons, and electrons, and the nucleus is the tiny dense center of the atom that contains the protons and the neutrons. And over 99% of the mass is in the nucleus, but it accounts for very, very little of its size. So the electrons occupy most of the space, and they're tiny. They're floating around the nucleus. The nucleus contains the protons and neutrons, so the opposite charge of the electrons and protons actually holds the atom together. The neutrons within the nucleus help the protons bind together because those opposite charges would repel, and the neutrons actually have a very stabilizing effect on the nucleus, helping the nucleus stick together. Now, the number of protons determines the element. Hydrogen atoms have 1 proton, helium atoms have 2 protons, and so on. And that gets the symbol Z. The number of protons and neutrons together is called mass number, whereas the number of just protons is atomic number. And so there is no number that just tells us the number of neutrons in something, but we can determine the number of neutrons by subtracting the atomic number, the number of protons, from the mass number, the number of protons and neutrons together. So if we take A, the mass number, minus Z, the number of protons, we do end up with the number of neutrons. It's also worth noting that atoms are electrically neutral. What I mean by that is they do not have an overall charge. The number of protons plus the number of electrons the number of protons and electrons is the same, and that means that there are the same number of protons or positive charges as negative charges because protons and electrons actually have equal and opposite charges. It is possible for an atom to become charged. That happens when an atom gains or loses electrons. When you have excess electrons, that means you've gained electrons, that's gaining a negative, and that ends up with an overall negative charge on the atom. Losing electrons, or a deficiency of electrons, means that we have an overall positive charge because there are more positive charges or protons than there are negative charges or electrons. And you can find the total charge of an ion, which is a charged atom, simply by subtracting the number of electrons from the number of protons. If you end up with a negative here, so if you say that there's something that has 10 protons minus 12 electrons, that's because you have 2 excess electrons, which ends up -2 or a 2 negative charge. If you end up with positive, then you have positive charge. And an electrically negative atom, or a negatively charged ion, is called an anion, whereas positive ions are called cations. Isotopes are not dealing with the number of electrons and protons, but rather dealing within a single element of how its mass can be different. So remember, James Chadwick discovered the neutron, and the neutron can vary without changing the number of protons, and that means the atomic mass can vary of a given element for different atoms. So we refer to the different atoms or different mass atoms of the same element as isotopes. So we refer to specific isotopes with their mass number. So this example, carbon always has 6 protons, that's what makes it carbon, but sometimes it has 6 neutrons, and that means it's got a mass number of 12 because 6 plus 6 is 12. 6 protons plus 6 neutrons is 12 particles in the nucleus, whereas if we added 2 more neutrons and had carbon 14, 6 plus 8 is 14, and we have 14 particles in the nucleus. Now, if I just say carbon, then I'm referring to the element carbon and any isotope, in fact, every isotope. It's the general form of it. And when we have a sample of carbon, it will actually contain all the different isotopes of it, although not equal amounts. It turns out that some isotopes are more common than others. Look at that in a minute. To shorten this up, instead of writing everything out, scientists use the shorthand where we use the chemical symbol. Now remember, a symbol is 1 or 2 letters. If it's 2 letters, the second one is lowercase, 1 letter it's uppercase. With mass number, charge if it has it. If there's no charge listed here, then it's not an ion, it's just the atom and there is no charge. There's equal numbers of protons and electrons. And down here is the atomic number. Although it's omitted or left out a lot of the time, because if I say helium, we already know it's got 2 protons. That's what makes helium helium. So mass number in the top left, atomic number in the bottom left if it's there, and charge in the top right. Also notice that the charge symbol, plus or minus, is written after the charge amount. That is the correct way to do that. So this says helium has, this is a helium-4 with a 2+ charge. So the helium-4 tells me I'm not talking about every isotope of helium. I'm just talking about the specific isotope of helium that has 2 neutrons. And I know it's got 2 neutrons because 4 minus 2 leaves me with 2. And this ion has no electrons left because in order for a helium to have a 2+ charge, it needs 2 more protons than electrons. Well, it only has 2 protons. So to get rid of the electrons, I've got to get rid of all of them. And then there's this weird thing called an atomic mass unit. Because atoms are so small and the particles that make them up are even smaller, talking about them in grams does not make any sense. So instead, a new unit was created based off of a carbon-12 atom. Basically, we said, all right, carbon-12, most abundant isotope of carbon, we're going to go ahead and say it has a mass of 12 AMU. And so dividing that by 12 gets us the mass of 1 AMU. Now we can measure all of our elements, our atoms, relative to that. And we can measure protons and neutrons relative to that. Now you'll notice protons are slightly smaller, less massive than neutrons. And electrons are way, way, way less massive. Electrons have about 1/2000th the mass of a proton. This will be important in a minute. So the atomic mass of a single atom is almost the same as its atomic or as its mass number. So we've got a lot of words that I've thrown at you lately. Atomic mass, mass number, atomic number. Atomic number, number of protons. Mass number, protons plus neutrons. Atomic mass is the weighted average mass of the different masses of all the isotopes of that element. So we use an average, and you'll notice that the atomic mass of an isotope is going to be slightly different than just the mass number because of the inclusion of electrons, because protons and neutrons have a mass that's not quite equal to 1, and as we'll see later if we talk about nuclear chemistry, there's some mass energy conversions happening in the nucleus. That's not a big deal, we'll look at that later. So you look at the periodic table of the elements and it'll show you the atomic number, but it'll also show you the atomic mass. And that atomic mass is a weighted average mass of all the different isotopes. And the way that's calculated is right here. Percent abundance of that isotope times that isotopic mass plus the percent abundance of the next isotope times its isotopic mass. And repeat that until you've done all of the different isotopes of that element. Yeah, this is just like when we say the average household has 2.3 children and 1.5 pets. You don't actually have 0.3 of a child. You don't have 0.5 of a pet. What you do have is an average. So if we look at the periodic table and we see that average, we won't expect any individual atom to have that mass. But if I have a group of millions of atoms, which is actually something that we work with, then on average they do have that mass.